In the last two videos for this chapter, we offer a definition and discuss the properties of the heat capacity of pure substances. We introduce the concept of molar and specific heat capacities and relate the magnitude of these quantities to the atomic or molecular structure of the substance. When we transfer a certain amount of heat, Q, into or out of a substance, we can measure a specific increase or decrease in the temperature, delta T. In the limit of small temperature changes, the ratio Q, the heat, to delta T, the change in temperature, is a constant C that is independent of the amount and the direction of the heat exchanged. This constant is called the heat capacity of the substance and depends only on the chemical composition, the structure, the phase, and the amount of substance considered. The heat capacity is actually directly proportional to the amount of substance. Hence, the heat capacity with units of joules per Kelvin, or equivalently joules per degree Celsius, is an extensive thermodynamic property of matter. Since the heat capacity is extensive, we can define the associated intensive properties of specific and molar heat capacities, which are the values often reported in thermodynamic tables because they are independent of the amount of substance considered. The specific heat capacity, which we will write as C sub S, is defined as the ratio of the heat capacity C to the mass m of substance considered. C sub S has SI units of joules per Kelvin per kilogram. In the chemical sciences, we prefer to report the amount of material in moles, so we define the molar heat capacity, written as C sub m, as the ratio of the heat capacity C to the number of moles. The molar heat capacity has SI units of joules per Kelvin per mole. When we heat a substance, such as a gas, we can actually carry out the experiment in two ways. We can heat the gas isobarically, that is, the gas pressure remains constant during heating, or isochorically, that is, the gas volume remains constant during heating. Isobaric heating is carried out in a cylinder sealed from the surroundings by a freely moving piston. The heat capacity measured under such condition is written as C sub P and is called the heat capacity at constant pressure. Obviously, we can define C sub Pm and C sub Ps, the molar and specific heat capacities at constant pressure. Conversely, isochoric heating is carried out in a cylinder where the piston is locked in place. The heat capacity measured under such condition is written as C sub V and is called the heat capacity at constant volume. Similarly, we can define C sub Vm and C sub Vs, the molar and specific heat capacities at constant volume. We will see in the next lesson that for gases, the magnitude of C sub Vm and C sub Pm differ from each other because at constant volume, heating of a substance does not require the substance to do work on the surroundings, whereas heating of a substance at constant pressure does. On the preceding slide, we said that the heat capacity of substances depends on the chemical composition, structure, and phase of the substance. Let us examine that statement further by considering for different substances the magnitudes of their molar and specific heat capacities. Note first that the substances are arranged in this table in order of increasing molecular size. Air is basically a mixture of oxygen and nitrogen molecules, which are both smaller in size than water molecules, which is itself smaller than ethanol, composed of 9 atoms. Ethanol is a smaller molecule than benzene, which has 12 atoms, and benzene is smaller than stearic acid or octadecanoic acid with its 56 atoms. So we first conclude that the molar heat capacity increases systematically with the size of the molecule. No such correlation can be found when considering the magnitude of the specific heat capacity of substances. To explain why the molar heat capacity increases with the size of the molecule, all we need to think about is the series of diagrams shown in the preceding lecture when we discussed the quantized energy levels for translational, rotational, and vibrational motion in the context of the Boltzmann distribution. Molecules of increasing size can find more ways to absorb thermal energy because such molecules have more chemical bonds, thus a larger number of vibrational energy levels. Larger numbers of energy levels in a given range of energy always leads to higher magnitudes of the molar heat capacity. When we consider the specific heat capacity of substances, we somewhat compensate for molecular size because the specific heat capacity can easily be shown to be the ratio of the molar heat capacity to the molar mass. Dividing molar heat capacity by the molar mass takes into account the size of the molecules. However, it does not take into account the structure and the chemical composition of molecules. This is why specific heat capacities have somewhat similar magnitudes. The only clear conclusion that can be drawn from the table of specific heat capacity values is that molecules which exhibit hydrogen bonding have significantly higher specific heat capacities than other substances. Water is indeed the substance with highest specific heat capacity and the substance with strongest hydrogen bonding. This fact has far-reaching implications for our life on Earth. For instance, think about the role of oceans to moderate temperature fluctuations on Earth as the Earth rotates around its axis and exposure to the sun radiation varies from daytime to nighttime.